Here at number 1, you're looking at a pattern involving squares. If you have algebra with Mr. Kinzer or Mr. Alexander, you'll have done a lot of these square patterns, and you're probably an expert who can help your classmates. So in step 1, you had a square that was 1 by 1, 1 by 1. In step 2, you had a square that was 2 by 2, 2 by 2. And in step 3, you had a square that was 3 units by 3 units. So hopefully you figured out for the first thing that asks you to make a sketch that the fourth step should have a square 4 by 4. 4 units by 4 units. And then it says down here, complete the table of the number of unit squares, this size, at each step. And it showed you step 1, 1 unit square, 1. Step 2, 1, 2, 3, 4, 4 unit squares. Step 3, these are all here, 1, 2, 3, 4, 5, 6, 7, 8, 9 unit squares. And now you've drawn step 4. So you're going to go ahead and say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 unit squares. And you're going to fill in the answer, 16. And hopefully you started to get a sense of a pattern. Maybe you sketched the 5th step and you said, okay, there are actually 25 squares. But at some point you could say, all right, to get from here to here, I'm squaring. 1 squared is 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 times 5 is 25, 6 times 6 or 6 squared is 36, 7 squared is 49, and whatever step number n, there are going to be n squared unit squares in the diagram. Now before we go on to step 2, I want to take a look at this pattern and connect it to some of the patterns we've looked at already in algebra. If you're not in algebra this year, you might not have looked at these patterns, but most of you are in algebra this year, and all of my students are. So let's take a look at some of the... All first semester we were looking at linear functions and linear patterns. And hopefully all of you know that linear patterns work by the rule y equals mx plus b. And an example of a linear pattern might go 1, 2, 3, 4, 5. For those steps, 1, 2, 3, 4, 5, we might go, I'm going to start with 4 and go by 3s. 7, 10, 13, 16. So what characterizes a linear pattern is that the differences at each step are always the same. To get from 4 to 7, I add 3. To get from 7 to 10, I add 3 again. 10 to 13 is plus 3. And 13 to 16, that's also plus 3. And linear patterns can always be written in this form. This one would be y equals 3x plus 1. The rule for getting this number from this number is multiply by 3 plus 1. The common difference here is always 3. And when I plug in 0 into this rule, if I went back, I would get out 1. So those are linear functions. We spent a whole semester looking at them. And then so far this semester, we looked at exponential functions. Exponential. And those were functions that could be written in the form y equals a times b to the x. And we said what characterizes exponential functions for a pattern, 5 steps again, is that they go up by the same ratio every time. So if I started with 4, and then I'm going to multiply by 3, so I'm going to say 12, 36, 36 times 3 is 108. And then 108 times 3 is 324. And what's happening here is that we're multiplying. We're not adding or subtracting, we're multiplying by the same amount every time. And this pattern could be written in the form y equals 4 thirds times 3 to the x. So those are the two types of patterns that you're already familiar with. So to recap, we know that linear functions grow by a constant difference. We add or subtract the same thing over equal intervals, or every step. And we know that exponential functions grow by equal ratios over equal intervals. At each step, you multiply by the same amount. So, how can we characterize this quadratic pattern, this pattern of squares, this square pattern? As a side note, notice that this n to the 2 is usually called n squared, precisely because this actually makes a square. The square pattern looks like is modeled by n squared. That's why we call n to the 2 power n squared. Anyway, let's look at the pattern. Well, first of all, let's see what are the differences here. From 1 to 4, I go up 3. From 4 to 9, I go up 5. From 9 to 16, that's plus 7. 16, 25. Looks like I added 9. 25 to 36, that's up 11. And maybe you're starting to see a pattern. 36 to 49, yes, the pattern works. That's plus 13. Well, it's clearly not a linear change. I'm not increasing by the same amount every time. That's for sure. But there is very much a pattern in the differences, just like there's a pattern in the differences for a linear function. A linear function would go up by the same amount every time. But this function, from 3 to 5, I went up 2. From 5 to 7, I went plus 2. 7 to 9, that's plus 2. 9 to 11, that's plus 2. And 11 to 13, that's plus 2. So I didn't go increase by equal differences over equal intervals. But the differences between the differences were the same. These aren't the same every time, but these are. So what characterizes a quadratic pattern, a pattern of squares, is that there are equal second differences over equal intervals. The difference between the differences is always the same.